In this video, we're going to go over some probability questions from past final exams of Math 105. Before we do that, we'll quickly go through some big results from our probability lectures. Because this is going to be a really quick review, we'll mention some things that are true without explaining why they are true. If you can't remember why they're true, it's a good idea to go back and review the lectures. The definition of a cumulative distribution function is given here. It looks a little strange with this x less than x, but remember what this means is, for example, f of 1 is the probability that my variable is less than or equal to 1, f of 2 is the probability that my variable is less than or equal to 2, and so on. The big X is just the name of our random variable, like the dice throw or choosing a random number. This less than or equal to, that's where the cumulative comes from in the name. And that gives us the property that this function is non-decreasing. The fact that this is a probability tells us that it always has to be between 0 and 1. Now the probability that x is less than or equal to infinity, that's 1. And the probability that x is less than or equal to negative infinity, that never happens, so it's 0. So indirectly, those lead us to these two limits. We use the cumulative distribution function to define the probability density function, and it's just the derivative. The PDF has some nice properties. The area under the curve gives me the probability of my variable being in a particular range. Because this is a probability, it's always between 0 and 1. So in particular, I could never have a negative area under the curve. And if I take the area under the curve from negative infinity to infinity, that's the probability of being between negative infinity and infinity, and of course that's 1. So that tells me the area under the curve over the entire real line of my probability density function has to be 1. We saw how to go from a cumulative distribution function to a probability density function when we defined probability density functions. But we can go the opposite way as well, again using this property. The cumulative distribution function, that's the probability that my variable is less than or equal to x, which is the same as the probability that my variable is less than or equal to x and bigger than or equal to negative infinity. So that's going to be the area under the curve of the probability density function from minus infinity to x. We use the probability density function to define the expectation or expected value of a continuous random variable. We define it as this improper integral. Let's think about what are the appropriate principles to apply to solve this problem. We want this function to be a probability density function. It should be a constant number when x is between minus 2 and 5, and 0 otherwise. Now, one property of a probability density function is that it's never negative. So it's 0 here, and 0 here, and some positive number here, k. Another property of a probability density function is that the area under the curve on the entire real line is 1. In our case, the area is 0 except in the interval from negative 2 to 5. Now we could compute this as an integral. We could just say this area is a rectangle, and I know the area of the rectangle, it's going to be base times height, which is 7 times k. So either way, we get that this is equal to 7 times k, and that needs to be equal to 1. So k is equal to 1/7. That's the only value of k that will make this function f of x into a probability density function. There was a second short answer probability question in 2017. In this question, we're given the probability density function, and we need to find the cumulative distribution function. So let's remember the cumulative distribution function. That's the probability that my variable is less than or equal to x. That's the probability that my variable is between negative infinity and x. And that's the area under the curve from negative infinity to x of our cumulative distribution function. So remember to go from the PDF to the CDF we take the area under the curve from negative infinity to x. In this case, our probability density function is e to the minus t times e to the minus t. We can solve this using a u substitution. I have this as an inside function, and its derivative shows up multiplied. So let's let u be minus e to the minus t. Then du is negative e to the minus t times the derivative of minus t. So du is e to the minus t dt. So e to the minus t dt, that becomes du, and e to the minus t, that's just e to the u. Now remember, when we're doing a u substitution on a definite integral, we need to change the bounds as well. If t is equal to x, then u is negative e to the negative t, that's negative e to the negative x. So my upper bound becomes negative e to the negative x. For my lower bound, t is minus infinity. What does that look like? U is minus e to the minus t, that's minus e to the infinity, that's minus infinity. So the lower bound doesn't change. This is an improper integral, so I need to replace that lower bound with a limit. My antiderivative is e to the u. I'm evaluating it from a to minus e to the minus x. The limit as a goes to negative infinity of e to the a is 0. So my cumulative distribution function is e to the minus x. Now this was a bit of computation, and so it's nice to do just some very basic checks to make sure that this makes sense. The first thing that should be true is if I differentiate my cumulative distribution function, it should give me my probability density function. If I differentiate the function e to the minus x, here's my exponent, minus e to the minus x. So the chain rule says I need to multiply by the derivative of that, which is e to the minus x. And this is exactly little g of x. So that bit works. We also have a general idea of the shape of g of x. It needs to have a limit of 0 on the left, a limit of 1 on the right, and it needs to be non-decreasing. So we can think about sketching this. And maybe let's do this in stages. E to the minus x looks like this. Negative e to the minus x is just the negative of that. So if I take e to the minus x, when x is 0, I have e to the negative 1, that's 1 over e. And then as x goes to infinity, this goes to 0. So as x goes to infinity, I have something that looks like e to the 0, and e to the 0 is 1. So I do have this limit off to the right going to 1. If I take the limit as x goes to negative infinity, my exponent goes to negative infinity, e to the negative infinity goes to 0. So I have the correct behavior on the left as well. So all of my behavior pretty well adds up. In April 2016, students were asked to find a constant that would cause the given function to be a probability density function. Pause the video, think about which properties of the probability density function you'll need to use, and see if you can find that constant. The property that's going to help us here is that the area under the curve of my probability density function over the entire real line has to be 1. Our probability density function only exists between 1 and 3, so we can assume it's 0 everywhere else. Between 1 and 2, it's this constant positive value. And then between 2 and 3, it's some quadratic value, a times x squared. So let's start thinking about the area under the curve. This constant value is 12 over 31. So the area here is 12 over 31. It's a rectangle with base 1 and height 12 over 31. Now let's think about the area underneath this quadratic portion. This is the area under the curve from 2 to 3 of a times x squared. So we can figure this out using the fundamental theorem of calculus, part 2. This is a over 3x cubed, evaluated from 2 to 3. That's a over 3 times 27 minus 8, which is a over 3 times 19. Now because the area under the entire curve has to be 1, this tells us 12/31 plus 19a over 3 is equal to 1, and now we just solve for a. So 3/31 is the value of a that turns f of x into a probability density function. The definition of the expected value of a continuous random variable comes from the probability density function. So we can think of this question as simply asking us to apply the definition of expected value. On the other hand, if we remember what expected value measures, there is a faster way to solve this problem than just applying the definition. So I'll show you two ways. Remember that the expected value acts as an average over many events. Let's visualize what would happen if I were to perform this random process a number of times. Let's start by thinking about our probability density function. At 0, it's a quarter, and then it's increasing as we go towards 1, and increasing as we go towards -1 in a totally symmetric way, because the absolute value of x has this even symmetry. I expect more values close to 1 and -1 and fewer values close to 0 if I were to run this experiment a whole bunch of times. And again, because our probability density function has even symmetry, I expect to have just as many close to 1 as I have close to -1. So if I were to average these events, I would expect every positive one was paired with a -1 of the same magnitude. So I would expect the average to be 0. So it's reasonable to expect that the expected value is going to be 0. But we can also compute expected value simply using its definition. The definition of the expected value of a random variable is the area under the curve over the whole real line of x times the probability density function. In our case, the probability density function is 0 everywhere except from -1 to 1. On the interval from -1 to 1, our probability density function is 1/4 plus 1/2 times the absolute value of x. So we just have to compute this integral. Absolute values behave differently when x is positive or negative. If x is positive, the absolute value just gives us x. If x is negative, the absolute value changes the sign. So we can write this as minus x, because minus a negative number is a positive number. With that in mind, I'm going to split this integral up into the part with negative x's and the part with positive x's. When x's are negative, the absolute value is negative x. So this integral has integrand minus 1/2 x squared. When x's are positive, absolute value of x is the same as x, so this integral has integrand plus 1/2 x squared. And now I just need to evaluate these using the fundamental theorem of calculus, part 2. So also if we use the definition of expectation, we find that the expected value of this continuous random variable is 0. After we find the expected value of this continuous random variable, we're expected to find its cumulative distribution function. The cumulative distribution function, that's the probability that our variable is less than or equal to x, which is the same as the probability that our variable is between negative infinity and x, which is the area under the curve from negative infinity to x of our cumulative distribution function. Let's pause for a moment and think about why this is restricted to numbers between 0 and 1. Cumulative distribution functions often end up being piecewise functions, sometimes with lots of pieces. In this case, our entire cumulative distribution function would have 4 pieces. So functionally what's going on is we're just being asked for one piece. So we're zooming in on values between 0 and 1. Now we're not asked the probability that our variable is between 0 and 1. We're asked what is the probability that our variable is less than or equal to x, where x is some number between 0 and 1. Remember, our probability density function is 0 for all values of t less than negative 1. So I can rewrite my integral like this. And then because x is somewhere between 0 and 1, I'm going to write this as the area to 0 plus the area after 0. This area is a little easier to find with geometry than it is to find with calculus, so let's do it this way. The area under the curve from 0 to negative 1 is a trapezoid. The base of the trapezoid is 1. Its height on the left is 1/4 plus 1/2. That's 3/4. Its height on the right is 1/4. So this area is 1/2. Now let's look at the area on the right. X is some number between 0 and 1. And we want the area of this green trapezoid. The base of this trapezoid is x. The height on its left is 1/4. The height on its right is 1/4 plus 1/2 x. Because x is positive, the absolute value of x is x. Altogether, this area is x times 1/4 plus 1/4 x. So this is our cumulative distribution function when x is between 0 and 1. We can do some quick checking that this makes sense. Because my values are equally likely to be positive and negative, the probability that our values are negative is 1/2. So if I plug in 0 to the function I found, I get 1/2 plus 0, which is exactly what I want. All of our values are less than or equal to 1, so the probability x is less than or equal to 1 needs to be 1. If I plug in 1 to the function I found, I get 1/2 plus 1/4 plus 1/4, and that is indeed 1. So these are good indications that the function we came up with are reasonable. To avoid a potential pitfall, one thing we know is that the probability x is less than or equal to negative 1 needs to be 0. If I try to plug in negative 1 to my function, I get 1/2 minus 1/4 plus 1/4, which is 1/2. So why doesn't this make sense? It doesn't make sense because negative 1 is not in 0 and 1. So we make no claims that this cumulative distribution function is correct for values of x except for values between 0 and 1. So don't get confused by trying to check it and finding something like this. Here's another question where we're asked to find the expected value after being given the probability density function. In this case, we don't have the nice symmetry that we had before, so we can't just jump to saying, oh, clearly it's 0. We need to use the definition of expected value. For this probability density function, everything is 0 for values of x less than 1. So I can rewrite this as the area from 1 to infinity, because the rest of that area is 0. And my probability density function is 3/2 x to the minus 5/2. It's an improper integral, so I should replace the upper bound with a limit. Now I evaluate using the fundamental theorem of calculus, part 2. As b goes to infinity, this term goes to 0, and I'm left with 3. The expected value of this random variable is 3. In this question, we're asked to find the value of a constant that makes this function a probability density function. So let's remember the relevant property of a probability density function. The area under the curve, the entire curve over the entire real line, has to be 1. That's the probability that my variable is between negative infinity and infinity. It's got to be 1. In this case, our probability density function is 0 everywhere except between -1 and 1. And on that interval, it's 1 plus k times the absolute value of x. Now there's two things we could do with this absolute value. I could split this up into the positive half and the negative half, as I've done before, or I could use the fact that it has even symmetry to say the left and the right are going to have the same amount of area, so I can just double the right. Both of these strategies will work just fine. I use the fundamental theorem of calculus, part 2. I need this to be equal to 1, so that tells me k is -1. It's a little unusual to see negative values in probability density functions, so let's sketch this to make sure there's no funny business going on. At 0, this is 1, and then it decreases. At 1, it is 0, and at -1, it's 0 as well. So we do not have an actual negative value of the probability density function, which is good. Here's a very similar question. We want to find the constant value that makes this into a probability density function. And again, it's 0 except for this restricted domain from -infinity to 1. So what we need is the area under the entire curve to be 1. And in this case, that area is 0 for values of x bigger than 1. So I can rewrite this area with this restricted domain. And on this restricted domain, my probability density function is k times e to the negative x times e to the negative e to the negative x. I can evaluate this, as we did at the beginning of the video, using a u substitution. As a goes to -infinity, e to the a goes to 0. I need this whole area to be equal to 1, so the value of k that turns this function into a probability density function is e to the 1 over e, or if you prefer, e to the -1. Here we have a different probability density function, and we're meant to compute the cumulative distribution function. Cumulative distribution functions often come piecewise. Let's sketch out the probability density function just to keep everything straight. For values of x less than 1, this is 0. For values of x greater than 1, well, at 1, this is 3. And then it decreases like 1 over x to the 4. The cumulative distribution function is the area under the curve from negative infinity up till x. So if x is down here, less than 1, this is just 0. I never choose values that are less than 1, so the probability of being less than x if x is less than 1 is 0. Now let's consider values of x that are greater than 1. In this case, the area under the curve is a whole bunch of zeros plus this piece here. So here is our cumulative distribution function. Now again, we can make some checks. It should be the case that the limit as x goes to infinity of my cumulative distribution function is 1. And indeed, that is the case. Now we're asked to find the expected value of yet a third continuous random variable. We're given the probability density function, so all we need to do is use the definition of expectation. Again, this isn't nice and symmetric, so there's no nice trick like it's definitely going to be equal to 0. The expected value is the area under the curve of x times the probability density function. The probability density function is 0 except between 1 and 4, and between 1 and 4, it's 2/9 times x to the negative 1/3. So the expected value is 2/15 times 4 to the 5/3 minus 1.